All right, hello. Let's take a look at problem 4, which proves to be a fun one. So in a refrigeration process, a fluid is throttled isenthalpically, constant H, in order to reduce its temperature. Therefore, when designing a refrigeration process, we desire to know the degree of temperature reduction that may be achieved for a given pressure drop for a specific fluid. The importance of this property leads to the definition of the Joule-Thompson coefficient μJt, where μJt is defined as dt dp at constant H. Okay, so I'm isenthalpically throttling a fluid, so I'm decreasing my pressure, and the effect of decreasing the pressure that I'm looking for is a reduction in temperature. Okay, so I'm looking for positive JT coefficients. So if μJt is positive, that means as pressure decreases, temperature decreases as well. Okay, so in A, we're asked to derive an expression for μJt as a function of Cp, Cv, Pv, and T. Okay, so we want to derive an expression for μJt that involves just PVT, Cp, and Cv. And then in B, we're going to be asked to evaluate the JT coefficient for the case of an ideal gas and for the case of a fluid in which the molecules don't interact but take up space, and use that to gain insight in terms of what makes a good refrigerant. Right? And so, this is fun because we're going to derive our JT coefficient or expression for a JT coefficient, in theory starting from a combined statement of the first and second law. And, with that expression then, we'll be able to use equations of state, which, for the case of an ideal gas, molecules don't interact and don't take up space, and then an equation of state in which molecules just take up space, and use that then to gain insight in terms of, well, what must cause a fluid to be a good refrigerant? What causes that temperature drop for a given drop in pressure? So fun, right? So let's do it. So if I'm looking at our expression, okay, there's a couple of things we can do. All right, and so I'm going to do it the first way, and I'm going to get stuck. Because oftentimes you just need to jump at a problem, see what works and doesn't work, and just collect yourself and have at it again. So if I think about how we've tackled problems before, here I have μJt as dt dp at constant H. And so I don't have a Maxwell relationship or heat capacity relationship that I can plug in. So the first thought that might come to mind would be to go get my fundamental equation for H, evaluate an expression for dt dp at constant H. So essentially get an alternative expression for dt dp at constant H and see if that gets us any closer. Okay, we're going to find that's not the case, but let's do it and see, and then let's try and come up with an alternative. Okay, so just in the interest of just doing it, right? So what I'm looking at is I want to calculate partial T, partial P at constant H. Okay, so a first approach might be, let's go back to our differential equation or fundamental equation for H and work out an expression for dt dp at constant H and see what that gets us. Okay, well, if I do that, okay, remember combined statement of the first and second law, du is TdS minus PdV. H is defined as U plus PV. Role of H is to flip the role of the conjugate variables P and V. Okay, so dH is TdS plus V dP. If I want an expression for dt dP at constant H, well, I have P here, right? So what I'm going to do is essentially work out dP dt at constant H, because dP dt at constant H would just be the inverse of dt dP at constant H. Okay, so if I divide my differentials by dt, okay, I can only differentiate with respect to one variable at a time. So here I need to hold another constant, which in this case is going to be H. Okay, and when I do this, okay, we end up with dH dt at constant H. Well, H is being held constant, so the derivative of a constant is just 0. That's going to be equal to T ds dt at constant H, T ds dt at constant H, plus V dP dt at constant H, where dP dt at constant H is what I'm after. Okay, but where I get stuck with this is when I look at the first term. Okay, now I have ds dt at constant H. Okay, and I'm kind of stuck with that because I don't have a heat capacity relationship I can substitute in for this, and I don't have a Maxwell relationships. Remember, Maxwell relationships are going to relate S to PV and T. Okay, so that term I'm just stuck with. And it's not that I can just go back to our fundamental equation for S and work out an alternative expression, because where would I get my fundamental equation for S to apply here is I would go back to my fundamental equation for H and resolve for S. All right, so I'm kind of stuck, right? So that approach didn't work. Okay, so then the other light bulb that goes off my head is when I look at this. Okay, here I have dt dp at constant H. Okay, so looking at this, it would be great, say, if I had an expression for H with independent variables T and P. Okay, and why that kind of light bulb goes off is by this point we've derived an expression now for the differential of H with independent variables T and P and several times. All right, and so if I could work out an expression for H with independent variables T and P, I could go and use that to try and work out an expression for this term. So let's do it. So let's rewind. Okay, let's rewind. Let's rewind and regroup. Okay, and let's try a different approach. Okay, let's work out an expression for the differential of H with independent variables T and P. Okay, so step one. I'm going to rewrite this as dH dt at constant P dt plus, now differentiate with respect to the second variable, dH dP at constant T dP. Okay, then I'm going to look to see if I can plug in a heat capacity relationship or a Maxwell relationship. Okay, and here I have dH dt at constant P, which is our definition of Cp. So dH is equal to Cp dt plus partial H partial P at constant T dP. I didn't have a Maxwell relationship or heat capacity relationship I could plug in for the second term. Remember, Maxwell relationships are going to relate S to PV and T. And so we're going to go back to our fundamental equation for H, work out an alternative expression, and see if that gives us an expression that we can work with in terms of plugging in Maxwell relationship or heat capacity relationship. Okay, so since we had it above, dH is TdS plus VdP. Okay, now I want dH dP at constant T. So I'm going to go through and divide my differentials by dP. Okay, I can only differentiate with respect to one variable at a time, so I need to fix a second. Or here I'm going to fix T, and then in theory all my differentials become curly. Okay, so I get that dH dP at constant T is equal to T ds dP at constant T plus V dP dP at constant T. dP dP is just 1. Okay, now looking, I have a ds dP at constant T. Now immediately I think about a Maxwell relationship because our Maxwell relationships are going to relate S, P, V, and T. So if I go over to our equation sheet, okay, let me start by writing down our pieces. Okay, ds dP at constant T. ds dP at constant T is negative dV dt at constant P. So I'll have negative dV dt at constant P plus V, and then I can plug that in. So I'm going to end up with dH is equal to Cp dt plus V minus T dV dt at constant P dP. Okay, cool. Okay, so now I have my expression for H with independent variables, T and P. Okay, so let's box this in. All right, so now if we get back to the task at hand, what I want to calculate is mu jt is dt dP at constant H. Okay, so mu jt is dt dp at constant h. Okay, so let's do it. Let's work out dt dp at constant h. So, okay, well, let's write out the full expression just for clarity. But we're going to go through and divide by differentials by dp, and then we're going to hold h constant. Okay, so cp dt plus v minus t dv dt at constant p dp. Okay, so I'm going to go through and divide my differentials by dp. Okay, I can only differentiate with respect to one variable at a time, so I need to hold the second constant. Well, here I'm going to hold h constant. Okay, and let's see what I have. So dh dp at constant h, well, h is being held constant, so that's 0, is equal to cp times dt dp at constant h, where dt dp at constant h is just mu jt. So actually, let me plug in mu jt plus v minus t dv dt at constant p, and then dp at constant h, dp is just 1. Okay, so solving then, I get that mu jt would be equal to, so if I bring that over to the left, I'd have a negative sign, but I could just switch this. So I'm going to write it as t dv dt at constant p minus v, right, just negative of that, divided by cp. So mu jt is t dv dt at constant p minus v cp. Cool. All right. So there's our expression for mu jt. And then using that, let's take a look at b. Okay. So basically in b, we're going to compare two scenarios. Okay. So we're not going to evaluate jt coefficient for fluid that's described by one of our cubic equations of state, because honestly that's a little difficult. We could do it, but a little tedious for this screencast. But what we are going to look at is we're going to look at the case of an ideal gas, in the case of a molecule which doesn't interact but occupies space. And so we're going to take our ideal gas equation of state, and we're going to replace the volume with the free volume minus the volume occupied by the molecule. And we're going to compare those two cases and see if we can use that to gain any insight in terms of what makes a good refrigerant. Remember, looking at this term, okay, what I expect is that if I'm isenthalpically throttling something, so when I'm throttling something, pressure is going to decrease, right? So dP is going to be negative. So when I decrease the pressure, I want temperature to also decrease. Okay, so I want dT to also be negative. So what I expect then is for a refrigerant is for dT dP at constant H to be positive. Okay, the greater the temperature drop for a given pressure drop, the larger the value of mu jt. All right, so you might say the bigger the mu jt, the better the refrigerant. Okay, now there are lots of other things to consider when designing a refrigerant, but just for argument's sake, the bigger the value of mu jt, the more refrigeration power. Okay, so let's do it. Okay, and let me add a new page after. Okay, but let's start here. Okay, so let's consider the case first of an ideal gas. Okay, all right, so let's consider an ideal gas. Okay, well, an ideal gas is characterized by the ideal gas equation of state. So PV is equal to RT. Okay, so let's look at this term. All right, so solving for V is equal to RT over P. So dV dt at constant P is equal to partial RT over P partial T at constant P. So P's constant, R's constant, so that's R over P dt at constant P, where this is just 1. Okay, so if I plug that in then, okay, I have that for an ideal gas, mu Jt is equal to, okay, T times, now this could be RT over P, since dV dt at constant P is R over P. So this is RT over P minus V over Cp. Well, equation of state for an ideal gas is PV equals RT. So RT over P is just equal to V. So you get V minus V over Cp is equal to 0. So for an ideal gas, we find that the Joule-Thompson coefficient is 0. Okay, which means an ideal gas makes a terrible refrigerant, right? So if I were to decrease the pressure of an ideal gas, so if I were to isenthalpically throttle an ideal gas, the temperature is going to remain constant. There's going to be no temperature change. Okay, and this makes sense because we've shown that for an ideal gas, the enthalpy is only a function of temperature. Okay, so changing pressure, we don't expect to have much of an effect or have an effect at all. Okay, so we find that the Joule-Thompson coefficient of an ideal gas is just 0. All right, so now let's consider our a fluid in which molecules occupy space. So let's just say occupy space, but don't interact. Okay, and so while in ideal gas we get P is RT over V, here we're going to write P is equal to RT over V minus B, where B is the volume occupied by a molecule. So rather than using volume, we're using free volume, the total volume minus the volume occupied by a molecule, right? Here on a per molar basis to make it molar. All right, so the derivatives I need to work out are going to be this partial V, partial T at constant P. Okay, nope. And so I need to know dV, dt at constant P. Okay, so let's get an expression here which is explicit in V. Okay, so I have P times V minus B is equal to RT. PV minus BP is equal to RT. PV equals RT plus BP, or V is equal to RT plus BP over V, or if we break it up, RT over V plus BP over V. Okay, and this is kind of cool. Wait, this isn't V, this is P. Yeah. RT over P, RT over P, then BP over P, right, that's just V, plus B. Okay, let me just make sure I haven't goofed anything up. So PV minus BP is RT, PV is RT plus BP, because I'm bringing it over to the right. V is RT over plus BP over P, or RT over P plus B. Okay, cool. All right, so essentially the actual molar volume is equal to that of an ideal gas, right? RT over P plus B, the excluded volume. Okay, the volume occupied by said molecule. All right, so then if I were to work out dV dt constant P, that would be, okay, I can apply the operator to these two terms and add them up. I'm going to write it as partial RT over P partial T at constant P plus partial B partial T at constant P. So dV dt at constant P is equal to, okay, P's being held constant, R's constant, So I have R over P, partial T, a constant P, right? I know that's just 1, plus partial B, partial T, a constant B, or P. Well, B is just a constant, right? So that's 0. So dV dt at constant P is equal to R over P. Okay, cool. Yeah, it's equal to R over P. All right, so then my Joule-Thompson coefficient, mu jt, is equal to, okay, well, it's T dV dt minus V over Cp. So it's going to be T dV dt at constant P. So it's going to be T times R over P minus V. And that's all over Cp. All right, so now let's try and simplify this animal. How do we want to simplify it? Well, I could do a couple of things. One, I could plug in V is equal to RT over P plus B, and I think I'm going to go with that. So we just showed here that if I solve for V, I get V is RT over P plus B. Okay, so this is RT over P minus, okay, so minus, and again, V is RT over P plus B. So this is RT over P minus B, right, because it was a plus B. Okay, and that's divided by Cp. So I'm left with then mu jt is equal to negative B over Cp. Okay, what does this mean? Well, we said B is a constant, right, and it's equivalent to the volume occupied, by a molecule on a per molar basis. All right, so it's the volume occupied physically by our molecules. Cp is our constant pressure heat capacity, all right? So dH dt at constant P. So we know our heat capacity is going to be positive, all right? So we have heat capacity is positive. B is going to be positive, right? It's the volume occupied by a molecule. So negative B over Cp then we know is going to be less than 0. So if I have a fluid in which the molecules occupy space but don't interact, we would predict a negative JT coefficient. Right? A negative JT coefficient would essentially tell us that we have an anti-refrigerant. That tells us that when we isenthalpically throttle the fluid, so when we decrease pressure at constant enthalpy, temperature is actually going to increase. Right? Remember, when we isenthalpically throttle, that means dP is negative, right? Because pressure is decreasing. And so a negative JT coefficient then would tell us that the temperature would actually increase, that dT is positive. So if I have an ideal gas, a system in which molecules don't interact and don't take up space, my JT coefficient is 0. If I use this equation of state, which we're using to represent a system in which molecules don't interact, but they do take up space by replacing the volume with the free volume, then what we end up with is a negative JT coefficient, which means that my temperature is actually increasing when I isenthalpically throttle it. It's like an anti-refrigerant. So what makes a good refrigerant then? Remember, the refrigeration power of a fluid would essentially be the larger the JT coefficient, the greater the refrigeration power. Well, what we haven't included in this discussion is the fact that molecules interact. So the missing piece of the puzzle is the fact that molecules interact. So it must be then that positive JT coefficients, which good refrigerants have, would result from intermolecular interactions, right? And presumably, the stronger the interactions, the stronger the JT coefficient, right? And so, good refrigerants. So the refrigeration power is going to, come from the fact that our molecules are interacting with each other. Okay, cool. And all that came from a combined statement of the first and second law and two simple models, one representing ideal gas equation of state, and then our second toy model assuming or trying to account for the fact that molecules take up space. Cool, that's it. We haven't done, or we didn't do an actual cubic equation to stay here only because it becomes a little more involved, kind of beyond this screencast. Hope that helps.